Hello everyone, this is Rick Feinberg. I'm the press officer for the American Astronomical Society, and I'm broadcasting today from Watertown, Massachusetts. I am not in Hawaii at the Extreme Solar Systems meeting. I wish I were, though, because I bet the weather's a lot nicer there than it is here in Boston. Extreme Solar Systems began over the weekend and is continuing through the end of the week. It's a meeting that's attracting something of order 350 of the exoplanet researchers from all over the world to discuss every aspect of exoplanet research on this very special week. It's the 20th anniversary of the announcement of the discovery of the first extrasolar planet orbiting a sun-like star. And 51 Pegasi b is now part of history, and believe it or not, we've been studying exoplanets for 20 years. So today, we've gathered some observers and some theorists together to talk about some interesting new results that are being presented at the meeting. I put out several press releases over the AAS press release distribution service. So journalists who are on that list have received those releases. The releases will be online at the presenters' home institutions within the hour. So if you didn't receive a copy, you'll be able to find it online shortly. So let me introduce the panelists that we have here today. They'll be speaking in the following order. So first will be Paul Callis from the University of California, Berkeley. We don't see Paul's face at the moment. We see his screen, but we'll see his face at some point. With Paul is Abhi Rajan from Arizona State University. There's Abhi. The two of them are collaborating on a project that they'll tell us about. Then we will have Thane Curry from the Subaru telescope of the National Astronomical Observatory of Japan. Thane didn't have far to travel for this conference since he's based in Hawaii. Then we'll have Jason Stefan from the University of Nevada, Las Vegas. And finally, I've invited Lisa Kaltenegger from Cornell University to provide some independent perspective and commentary on the results that we'll hear today. Lisa, as many of you know, is one of the leading lights in exoplanet research and is often sought out for her very well-informed opinions about what's going on in the field. Another person whose face you see down there is Scott Idem. Scott is our American Astronomical Society IT director, and he's in the room there in Hawaii to help us out of any technical jams we get into. So with that, I would like to turn it over to Paul and Abhi to tell us about a disk that they've resolved around a star using the Gemini Planet Imager. So I'm going to turn it over to Paul. So Paul, make sure.
All right, thank you very much, Rick. Hopefully you can all hear me. It's exciting to be here. These meetings usually have a lot of exciting results, and what we're presenting today are some new discoveries made with the Hubble Space Telescope and the Gemini Planet Imager, just published in the Astrophysical Journal about 10 days ago. We're part of a team called the GPI Exoplanet Survey Team. We're using the Gemini South Telescope in Chile with an advanced adaptive optics system and chronograph, which blocks light from bright stars, and we're searching for planets. Part of this program has to do with the disks of comets and between comets. These are called debris disks. Every planetary system has something like this, and when these stars are very young, these dusty debris disks are very prominent. And when you look at their structure, the idea is that you may be able to understand the geometry and the architecture of a planetary system if you could resolve the structure, if you could make a map of it. And this is very difficult because the dust is faint and the stars are bright. Here's a comparison of what Hubble on the left can do with a dusty debris disk and what the Gemini Planet Imager is capable of on the right. This is you can see a loop of nebulosity around the star. The star is in the middle. It's blocked by a spot. That loop of nebulosity is a dusty comet belt, roughly 80 astronomical units from the star. And you can see that our ground-based capabilities are now exceeding what the Hubble Space Telescope can do. So this is a tremendous breakthrough in what we can do in terms of detecting extrasolar planetary systems.
Okay. Hi, this is Avi. Just let me present something about this particular system that we're talking about today. It's the star's number is HD 106906, and what we have over here is the companion. There is a companion to the star. As you can see in the image on the slide, the planet was actually discovered to be about 650 AU from the star. Now, to give you a comparison, 650 AU is about Pluto is only about 40 AU from our sun. So this is a star that's about 15 times further from. This is a planet that's about 15 times further from its star than Pluto is from the sun. The host star is a spectral type of F5, which means that it's about 1.5 times more massive than the sun, and it's about 300 light years away from us. So, and it's very, very young. It's only 13 million years old, which means that the planet is still radiating the heat of its formation. The system was interesting to us because we had already detected dust surrounding the star in a paper by Christine Chen in 2005 using the Spitzer Space Telescope. But in that result, all they had was unresolved photometry. They just saw the signs without actually getting an image of the disk. And so we were very interested in going after the star and trying to actually detect the disk and see what it looks like in an image. And the planet was actually detected almost 8 or 9 years after the original debris disk was detected by Vanessa Bailey at University of Arizona. And one of the big questions with this companion is it something that formed like a planet close to the star and then was ejected out of the system? Or is it something that formed like a star and just formed at the same time as the star itself as a binary star system? And so it's there's different results that can come of these two different formation mechanisms.
Okay, so that was an open question for almost a year, or just over a year, and now with these new results from GPI and the Hubble Space Telescope, we sort of know and have an answer to what may have been happening here. The inset, this red image here, shows our GPI result, where we're really probing very close to the star. That linear feature is a loop of nebulosity. It represents the size of the planetary system. It's roughly 50 astronomical units in radius, slightly larger than our own solar system's Kuiper belt. And you can see it's tilt-oriented roughly left to right, and it's seen almost edge-on. So now we know how the planetary system is oriented from this GPI image. But then we actually discovered that the Hubble Space Telescope had observed the system, and we reanalyzed the data. And it turns out that the Hubble Space Telescope has also detected the disk on a much larger scale. And this is the blue area in the background. And the central region is blocked. You can't see as close to the star as you can with GPI. And what you see is highly asymmetric nebulosity. It's very faint and subtle. I've tried to indicate where it is with these lines. On the left, it's vertically fat, and on the right, it's vertically thin. And I've labeled this debris disk with this line that says comet plane. And that arrow points to the extrasolar planet 10696b, and you can see that the planet is misaligned with the plane of the comet system. So we think that the whole system has been recently disturbed by some violent gravitational interaction, though we are not sure what exactly happened. Planets don't form outside of the plane of the planetary system. On the left is an ALMA image of the disk around HL tau, and that disk is very close to the star, and most planets would form in that disk very close to the star. HD, our planet is not only far from the star, but it's tilted away from the plane of the disk. So maybe the planet formed just like a star, which is represented on the right. These are theoretical simulations where objects collapse from a primordial cloud of gas and dust. And therefore, it's possible HD 10696 formed very far from the host star. But what we think we see now with these new images, 6906b did form in a disk very close to the star, just like you see in the GPI image, but something recently happened that kicked it out to these great distances. Having said that, we then reasoned, well, if the planet was interacting with the central debris disk, could it have captured its own circumplanetary material, as you can see in this artist's illustration on the left? So we did 3 experiments to test this idea using the existing data.
Okay, so the 3 experiments that we did were looking to see, if you remember the HST image, the companion is actually visible in the HST image, and so the planet's there over there. So what we tried to do was look at the profile of the planet in that image and compare it to the other point sources or stars that were in that image. And what we were essentially trying to do was see if it looks the same. And the left panel in this in the slide actually shows you that the 106-906 profile appears to be slightly extended, or well, essentially different from the other the stars in the image. Now, this was one clue that suggested that there's something interesting going on with this planet, and so we said, all right, let's look at a few other objects in a similar that are similar in age, similar in mass. Because we also noticed that theoretical models appear to predict a different brightness for the companion in this in the HST wavelength of 606, which is about 6,000 angstroms. And so when we did this comparison, the figure on the right essentially shows that there are only 2 objects. So the figure has several planetary masses, and what we have is a color which is 2 different wavelengths. You look at the planet in multiple different wavelengths, and you estimate a difference, which is called a color. And we compared the colors of these companions to models, and then we looked at whether the models were able to do a good job fitting the companion colors. And essentially what we found was there were only 2 objects, with one being our own, which is 106-906, and the other being FW tau B, that showed an excess red color above that 0 dashed line. And so what these 3 different experiments essentially showed was that 106-906 does seem to show some kind of reddening and some kind of extended profile, all of which are suggestive of a some kind of ring or a disk around this companion. essentially because FW tau has actually got a very, very cleanly resolved disk with ALMA as well. And so it doesn't seem to show the kind of reddening that FW tau does, but these different pieces all seem to point towards the same conclusion that there might be some material around this companion.
Okay, so it's very exciting to possibly have circumplanetary material. The evidence is tentative, and we think that we can get follow-up observations, possibly with Hubble Space Telescope, to confirm or validate this hypothesis of circumplanetary material. And this whole picture of a dynamically disturbed planetary system is tremendously exciting to theorists and also to people who study our own solar system, because it's thought that early in the evolution of our own solar system, about 4 billion years ago, our own planetary system had a violent rearrangement before it settled into its currently stable configuration. Thank you very much.
Okay, thank you very much. That was Paul Callis from University of California at Berkeley and Abhi Rajan from Arizona State University. And we're going to move on now to Thane Curry from the National Astronomical Observatory of Japan. And Thane, I think you should be able to share your screen now.
Okay. Okay. Let me know if you're able to see it. Let me know if you're able to see it. It's still showing me. Okay. So I'm just okay. Mm-hmm. Mm-hmm. Okay.
Very good.
Now is it?
You should maximize or put that into presentation mode.
So now is it just showing the?
It's showing everything, including the outline and the notes.
Okay. Yeah. So I should show in presentation.
Correct.
Okay. Presenter view. Yes.
Go to regular view.
Okay.
Let's do slideshow and just from start should find.
Okay. That. Yeah. Okay.
Do share screen again. Sorry.
Entire screen.
We'll do entire screen.
Okay. Okay.
There we go.
There? Okay.
Yep, that's perfect.
Okay, so excellent. So my presentation is divided into two parts. And so it's all under the rubric of extreme exoplanet imaging. So first I'm presenting detections of at least one, possibly two, baby Jupiter-like planets still actively forming, surrounded by their natal clouds of gas and dust. This is data obtained with the Gemini Planet Imager as well. And this is in a system we think resembles an infant version of the first directly imaged system of planets discovered using the Gemini North and Keck telescopes on Mauna Kea. Second, I'm describing what I think is the next step in exoplanet direct imaging, pivoting off new discoveries like these and like those that Paul and Avi just presented. In particular, I'm discussing the commissioning of a new instrument on Subaru atop Mauna Kea using state-of-the-art technology, and this is called the Subaru Chronographic Extreme Adaptive Optics project. And I'll describe the exciting opportunity for potentially imaging a terrestrial planet or on a nearby star if we're able to put SCUXEO in combination with a 30-meter telescope sometime about a decade from now. So to give you some context, for a long time, for human beings have at least known about the existence of other planets in our own solar system for thousands of years. But it was not until about 7 years ago that astronomers reported the first images of planets orbiting other stars. So HR8799 on the left, and Fomalhaut on the right, discovered by Paul Callis, who's one of the previous presenters. Fomalhaut B is made visible by light being reflected off of circumplanetary material. The object on the left, HR8799, hosts the first directly detected planets, meaning that we're actually seeing photons from the atmosphere of a planet. It also hosts the first image multi-planet system. And then 2 years after its first discovery, we are able to see a fourth planet. So this is an updated image of this system attained with the Keck telescopes in about 2012. And combined together, they orbit the star between about 15 to 70 astronomical units and resemble a sort of scaled-up version of our own solar system. So we think we may have found an evolutionary precursor to the HR8799 planetary system, a star with similar mass but far younger, that probes what these kinds of systems may have been looking like while the planets were still in assembly. This star is named HD 100546. What we're showing here, Hubble Space Telescope, where we see the star being surrounded by a very bright, massive protoplanetary disk, the sort of natal material from which planets form. This system has a lot of structure, like has spiral arms that are often interpreted as evidence for embedded growing planets. And actually, several years ago, a candidate planet was identified around this star. We took additional observations of this system with the Gemini Planet Imager. Our observations first recover this system in the near infrared, and we're able to combine these data with previous data to suggest that this candidate planet is embedded in a disk. It actually affects the planet to be, and it's probably just a few times more massive than Jupiter. So it's a bit of a scaled-up version of Jupiter, sort of like the outermost HR8799 planets. Additionally, we identify evidence for a second candidate, more massive planet in the system at about 14 AU separation. So roughly the separation between the Sun and Uranus in our own solar system is shown here. And so we see these planets here. We have one that's confirmed at about 47 or about 50 astronomical units, and the candidate one at about 14 astronomical units. This roughly spans the range of separations around which we see planets orbiting HR8799. And we suggest this might actually give us a window into understanding how the system may have looked like when it was still in the process of forming. And we can give further clues if we analyze these data in more detail and we compare the observed brightness of those planets and more predictions for the brightness of planets from atmosphere models, and also models that try to probe what these kinds of systems should look like when they're still in the process of forming. So this is showing our GPI image again for HR8799b, and this is the particular system we're able to analyze in detail. Namely, if you look more carefully, we see something very peculiar. We compare it to models for planet atmospheres, and these are shown in green and in blue. Those are the two lines there. So the green shows a limit where we assume there's not any clouds or dust in the atmosphere of a planet, and the blue shows the extreme limit, where the planet atmosphere is filled with dust and is a very cloudy object. What we see is that our protoplanet, HD 100546b, is extremely red compared to either of these models, and its emission, or rather its relative brightness at different wavelengths, cannot be easily explained by models for planet atmospheres. Instead, what we see is that its colors are best explained by a combination of a planet emission source, so atmospheric emission from the planet, plus a massive accreting circumplanetary disk. And those are the two dashed lines that we see, different models that predict the brightness of a planet plus circumplanetary disk system. We see a good correspondence between these models and the data, and this suggests that we're actually seeing, a planet that's still accreting material. This is still accreting material roughly at the rate of about 10 to the minus 6 or 10 to the minus 7 Jupiter masses per year. So this, I think, is an example of the kinds of new systems that we can see with the current suite of dedicated exoplanet imaging instruments like the Gemini Planet Imager. So then what does the future hold? Well, I think this is extremely exciting because the future is being driven by systems like GPI and also others like the one I'm involved with, which is the Subaru Chronographic Extreme Adaptive Optics project. So this is a dedicated planet imaging instrument being tested right now on Subaru. It's powerful because it corrects for atmospheric turbulence that blurs our images of planets orbiting nearby stars with extreme precision. So it's able to de-blur those images and reveal the light from objects located very close to the star. Additionally, it has a suite of chronographs to be able to block light from the star to further suppress it so we can see very faint objects, and also new detectors with extremely low read noise. So we can again identify extremely faint objects, lower and lower mass planets around nearby stars. So what is particularly exciting is that this object, or that this system is just coming online, and we're just now starting to be able to take science data for SCAXIO. This is an image we've obtained from our commissioning run of one wide separation super Jupiter planet that is far sharper than the previous images of the system by at least a factor of 3 or a factor of 4. And in the next couple of years, we should be at full power with this system on Subaru. And I think this presents an incredible opportunity because very soon, and we're starting to see this now, we're not just limited to imaging planets that are scaled up versions of Jupiter, but we're starting to bridge the gap between the kinds of planets that we can first see and the planets that are existing on the solar system. In fact, within a decade, perhaps even Earth-like planets might be imageable on the largest ground-based telescopes like the TMT on Mauna Kea. So a lot of people think that you need to go to space in order to image a terrestrial planet around a nearby star, but in fact you might be able to do this from the ground. And in particular, if you combine something like TMT with the capabilities of this instrument that we're now commissioning, you'll be able to see qualitatively different kinds of planetary systems, and perhaps planetary systems that resemble our own home. So what I'm showing here to end is a contrast plot. So this is showing the relative brightness of a population of simulated rocky Earth-like planets around stars with different temperatures, spectral types, and masses. And the circled region identifies the predicted brightness for rocky terrestrial planets around nearby low-mass stars like M stars, the most populous and most abundant stars in our galaxy. And if we compare that to what we think we might be able to do if we combine the ability of SCAXIO to deblur images and the large aperture of TMT to give us greater leverage to be able to image closer and closer to the star, we see that it's possible that we might actually be able to image these kinds of systems. So perhaps within the next decade, we will be able to image planets with roughly the composition of the Earth, at roughly the separation that the Earth is from the Sun, or at least relatively speaking for these stars. We'll be able to see them from the highest point or the tallest mountain on our own planet.
All right, very good. Thank you, Thane. That was Thane Curry from the Subaru Telescope, National Astronomical Observatory of Japan. And now we're going to move on to Jason Stefan from University of Nevada, Las Vegas. So we need Jason to share his screen. And unmute your mic. We're getting there. By the way, we're going to be taking questions by text, and we'll answer them out loud, so you don't need to try to answer any of the questions by text yourself right now. We'll get to those when we're finished with the presentations. All right, I'm going to turn it over to you, Jason.
Okay. Well, thank you for this opportunity to present some of the results that we've been working towards. This is work that's done by myself and my collaborator Gongji Li from the Harvard Smithsonian Center for Astrophysics. The motivation for our study, this is a theoretical investigation, so unfortunately I don't have any beautiful pictures to show, but you can use your imagination a little bit. One of the things that was interesting that came out of the Kepler mission a few years ago was the discovery of planetary systems that had multiple planets that were very close to each other. So this graphic shows the list of planetary systems where you have neighboring pairs of planets in order of their separation. So these are the systems that have planets that are the closest together of all of the 5,000 or so planetary systems that have been discovered by Kepler. At the top is our own solar system. These planetary systems have been rescaled so that the inner planet in the closest pair is at the same distance as the Earth. So if you zoom in, for example, you can see Venus, Earth, and Mars on this top row, and you can see below it a representation of the Kepler systems, but stretched out to the size of the solar system. When we had first discovered these planets, kind of the poster child is this fourth one down. That's the Kepler 36 system. And the Kepler 36 system is a pair of planets that are near the 7 to 6 mean motion resonance, which means when the inner planet goes around 7 times, the outer planet goes around 6 times. Their orbital distance when they're closest together is only 10% apart from each other. So if one was at 1 AU, at the distance of the Earth from the Sun, the second one would be at only 1.1 AU, which is very close together. It's about 40 times the distance from the Earth to the Moon, where if you compare, for example, the Earth to Mars, we're talking about a possible manned space mission to Mars. That's 200 times the distance from the Earth to the Moon. So these planets that Kepler is observing, if they were stretched out, if the system was scaled up to be the size of the solar system, they would be 5 times closer to the Earth than Mars is to the Earth. So you can imagine with the Earth in the habitable zone, and the habitable zone is marked on this graphic by the vertical dashed lines. So the Earth is near the inner edge of the habitable zone in the solar system, and Mars is close to the outer edge of the potentially habitable zone in the solar system. The reason that Mars isn't habitable now is because it's so much smaller than the Earth that it can't retain an atmosphere. If Mars wasn't quite such a wimpy planet, it would be able to potentially have an atmosphere that could support liquid water on the surface. But you can imagine these systems that have been discovered by Kepler where the planets are so close together. You could have multiple planets all habitable simultaneously in the system. And so that got me thinking, and Gongji and I have been discussing, what kinds of implications would this have for life given the dynamics that you have in these kinds of planetary systems? When you have planets that are this close together, their gravitational influence can be quite a bit stronger than the influence that the planets in the solar system have with each other, just because they're so much closer together. So to give you another idea of what this would look like, if you were to see one of these planetary systems from the surface of the Earth, this is a picture. You have the full moon on the left side, an Earth-sized planet at 1.1 AU, which is the effective distance of the two planets in Kepler 36, would look. And on the right is Mars doing its best to show up in the sky. You can see, when you look at Mars, you can see a small disk in the sky. With binoculars, the disk is quite a bit more apparent. But you can see here that the kind of a companion Earth in the position of some of these systems that we've seen with Kepler would actually show up readily to the naked eye. You'd be able to see clouds, you'd be able to see continents on the surface. You can imagine if Galileo had seen something like this, looked at something like this through his telescope, you could communicate between these two planets for hundreds of years before you could ever have a space program that could deliver a living person from one to the other, or a robot if you prefer robot visitations. So there are a number of things going on with our own Earth that have implications for its habitability and also for life beginning and evolving on the surface of the planet. Two of them in particular are the Earth's obliquity. The obliquity is the angle between the Earth's spin axis and its orbital plane. So on the Earth, that's the 23.5-degree tilt of the Earth's spin axis that gives us the seasons. If the Earth's spin axis changes dramatically, then you can have significant changes to the surface properties. You can cause ice ages. If the Earth were to be tipped over completely on its side, then you would have a very different habitability. It would be much more difficult to grow corn in Iowa if the Earth's tilt was much different than it is now. And the Earth's obliquity, or this tilt, does evolve with time, and it's been theorized that some of this evolution of the Earth's obliquity is actually responsible for the recurring ice ages. Another thing that's been studied in the solar system is the possibility of life originating on Mars or on a different planet, Mars in particular, and that life being germinated on the surface of the Earth through the impact of asteroids on the surface of Mars, ejecting a bunch of material, and that material traveling through space, landing on the Earth, and then seeding life on the Earth. What's shown here is an image of a Martian, it's an image of a meteorite that is known to be of Martian origin, and it shows things that look as though they may have been bacteria. So we have a sample of order 100 meteorites that we know come from the surface of Mars, and so we know that material can be ejected from the surface of one planet and delivered to the surface of another. So when you have two planets in the same system that are quite a bit closer together, that increases the chances of this kind of lithopanspermia, material being ejected from the surface of one planet through collision and deposited on the surface of another planet. So we did an investigation of these two different effects. When you have multiple planets in a system, do these strong gravitational interactions cause the obliquity of the planets to flop around a lot? Because if they do, it makes the climate significantly less stable. And it's a lot harder to have agriculture on a planet where the climate is not stable. And we also looked at the possibility or some of the effects of collision material being ejected off the surface of one planet and deposited on the other. So an example of some of the things that we investigated regarding the obliquity of the Earth, or of these sister Earths in these multi-habitable systems. We looked at the system in isolation to see if you just have these two planets in isolation, do they affect each other's obliquities in ways that would be detrimental to the development of intelligent life. We also looked at embedding the same pair of planets in the solar system to see if the perturbations from the other planets caused deviations to the planet's obliquities, or the spin axis. And we also looked at the possibility of having a close pair in a system if that would affect an isolated habitable Earth in meaningful ways. It turns out that in all three of these cases, the variations in the spin axis are not different than the planets in our solar system as they are now. That having these planets close together does not adversely affect their climates because of large obliquity variations. In other words, the climate is would be no worse in these systems than it would be in the solar system as we have it now. In terms of panspermia, we did a suite of simulations that looked at the ejection, the collision ejecta coming off of the surface of one object and being delivered onto the surface of the other. We did a few hundred simulations that comprised over 500,000 particles, looking at whether mean motion resonances or strong dynamical interactions between the planets affected the possibility of life-bearing material being transferred between the two, and also looking at different initial conditions to see if basically what kinds of properties in terms of the energy of the collision that produced the ejecta in the first place have on the probability of delivering this material from one planet to the other. The conclusions that we drew from this theoretical investigation are as follows. First is that the obliquities, and hence the climates on these planetary systems, are as stable as they are in the solar system. So you're no worse off having a neighboring planet that's also habitable or in the habitable zone. And it turns out that our study of this panspermia is that life is more likely to be shared among the planets in these multi-habitable systems than they are in the solar system. So you can imagine the biological family tree having roots and branches on both planets simultaneously. You could have microbial life that has very similar DNA on the surface of both planets at the same time. Because the planets are so much closer together, the initial collisions that produce the ejecta would be much lower energy, which means that you're not going to vaporize the life in that collision ejecta from the beginning. Also, the time of transit between the two planets in the system is significantly less than it is between planets in our own solar system. And so you have, I mean, two of the issues that you would confront in delivering life-bearing material from, say, Mars to Earth is one, that you have collisions that are more energetic, and so you may vaporize the life or destroy that life or biological material at the time of the collision, and also the transit time between the collision itself and depositing that material on the surface of a different planet is much larger in the solar system because the planets are farther apart. And in many cases, you actually have to involve somewhat exotic dynamics in order to excite the orbits to the point where they can be deposited on other surfaces. That doesn't exist in these multi-habitable systems where the planets are so much closer together, because the delivery time is significantly shorter. Measured in thousands of years instead of millions of years. In addition, one of the other things that we found, and I'm going to back up a slide, you can see on the image on the left, so this is a face-on view of the system and an edge-on view of the system. You can see in the image on the left that you form caustics, you form very high-density regions of the collision ejecta. This is a natural consequence of the way that material comes off the surface of a single impact. And so what you actually have is streams of debris that come off of the surface of the planet. It doesn't fly off in completely random directions. Rather, the stream of debris will lengthen out over time, but the material will still follow very similar paths. And so when you have structures like this, if the second planet or the destination planet plows through one of those streams, you would deposit some of this life-bearing material across the surface of that planet simultaneously. And that would give you an increased probability of seeding life across the surface of the destination planet from a single impact on the source planet. And so you have excess probability of delivering multiple life-bearing rocks across the surface of the destination planet. All of these things combine to make it such that life in a multi-habitable system may have a higher probability of developing, because the burden of surviving some of the catastrophic events is shared between multiple planets in the same system.
Okay, thank you very much, Jason. That was Jason Stefan from the University of Nevada, Las Vegas. And now I've asked Lisa Kaltenegger from Cornell University to give us a little perspective and some commentary on the results that we've just heard. As I mentioned at the outset, it's been 20 years since the discovery of the first exoplanet around a solar-type star, we seem to have come a rather far distance in that 20 years. Lisa?
I completely agree with you. So I am happy to give my take on this. So at Cornell, we have the Institute and I'm the director. And so we the planet as a house system outside. So what you actually, I'll start with the first, what Paul and Avi found this really interesting oddball configuration, if you want. It's something that surprises scientists who really don't know how this actually fits together, the cometary plane and the planetary object far away. How did they form? How did it come out? All of these things, real pieces. Because if we get surprised, we learn some. And then if you see things presentation where we have baby Jovian planets, and I love that term, so we have baby Jovian planets that we see forming, and we basically start to see an infant version of a system where around a different star, but pretty similar, we have a directly imaged systems of, if you want, adult planets. So what is really important here to me is that we're starting to see the steps from this really first steps of forming the planets to where we see the disk disappearing and we see these planets come out more and more, still very young. This is the system that he was talking about as the first image system with the 4 planets he showed initially. But basically these steps, how does it actually come about that planets form? And then in the long run, these ones are all much too big to have life because they're more like Jupiters and hot Jupiters. But in the long run, that also will tell us how the small planets form in the systems. Link there comes in, what's really interesting, because again, we had our own solar system, and as you said 20 years ago, we thought this is what we would find when we're looking out. And now 20 years later, we found these amazing diversity of planets out there. And yes, we can spot the big and heavy ones and hot ones easier because those are easier to pick up. But among those, and especially also the Kepler results, we already have the first planets that are within what we call the habitable zone, where we can have liquid water on the surface. And again, that doesn't mean that it's the only place where you can have life, but it means this is where we can pick up or find life by just looking through our telescope. And that brings me to the third presentation. By the way, I just wanted to mention in Thane's presentation, I love the optimism that we can do this in about a decade from the ground, because I think living in the time where we can actually spot Earth-like planets with huge telescopes, granted it's going to be a lot of work and we're going to have to build these things, but living in the time where we can spot them from space. That's why we're building JWST, and the TESS mission that's going before and looking at all these small red stars to look at the closest by Earth-like planets around small stars. But living in a time where we can do that, I think that, for me personally, is fascinating. The first time in human history that we can actually find other worlds like ours if they exist there. And that brings me to the last presentation with Jason and Stefan, where I love the imagery that if you had a planet closer by, you could actually see surface features potentially if it's not completely shrouded in clouds. And of course, you cannot just put our own Earth there, because if it's further away from the star, it could have completed properties and so on and so forth. As we see Earth mass Venus, that gives us like a range of interesting properties for rocky planets. But spotting it in the sky, as he said, Galileo would have probably been even more motivated to go and find out what's going on this planet. In our own human history, we were super fascinated by Mars, especially when we saw all these candles on Mars and we thought that there was big civilizations. But what's interesting in this whole thing too is so we find a lot of multiple system with multiple planets, even very close by ones. And again, Jason actually stretched them out because, of course, they are much closer to the star. That's where Kepler has most of its observing power. But what it actually shows us is that our solar system, again, is not even the most tightly packed thing. We thought most things would be like our solar system. They are really not. We find a huge diversity in planets, with small rocky planets very close together and further apart. And one of the ideas that is very interesting here is to say, well, what would happen to the climate on a planet if they were close together? And they found that it actually wouldn't be that different. But having said that, even if the climate would be different, the funny part is that when we talk about corn in Iowa, and I really like that that comparison, corn in a different Iowa on a different exoplanet would have evolved for whatever climate, and so it would be probably a little bit different corn. But the good thing is that even a very close other planet wouldn't actually destabilize your climate that much. That's what they found. And then, of course, the open question is, how does life start? And this is also one of the things I'm extremely interested in when we're trying to figure out how the conditions for life on other planets could be like. And it could be that there's something where life actually shares, or material gets shared between planets. So one of the questions are, in the very long run, when we find life on other planets, we'll have to look very closely if it looks very similar. And that brings us back to our discovery, or our look for life on Mars. We discover life on Mars, we really would like there to be some. If it looks exactly like life on the Earth, does that mean life started on Mars and just went the same evolutionary trail? Or did it mean we brought it there? And so all of this is unraveled in our own solar system. And by looking at other solar systems and hopefully finding signatures of life within the next decade, I think we're going to be in for a lot of surprises as these oddball systems show us. But these 20 years have brought us from thinking the solar system and the first really weird planet, 51 Pac, that was found 20 exactly this week, or published 20 years ago, to a diversity of planets that I think we could have never imagined, and to a lot of scientific insight that now makes us understand a little bit more how we fit in this amazing cosmos. And we look out, and within the decade, hopefully, we'll find the other planets that have habitable conditions out there. Back to you.
Okay, thank you very much, Lisa. That's Lisa Kaltenegger from Cornell University. So, according to my computer screen, we have a couple of questions that have been submitted from viewers. So what I'm going to do is I'm going to select one. I don't know what that means. I think that means that some of you may be able to see the question, but I'm going to read it out loud. This question comes from Monica Young at Sky and Telescope, and although she doesn't say, I gather that it is for Paul or Abi about their the planetary system that they were looking at with the dust disk that was at a different inclination than the planet. Is the system disturbed by a nearby star or by something smaller? And if a nearby star, is there a candidate culprit?
Indeed. This is Paul Callis. That's a great question. The bottom line is this work is so new, we don't have a candidate culprit. We have to do probably many years of study to understand if any of the nearby stars are moving with HD 106-906. That is to say, if two stars are moving together in space, then they're likely close to each other and physically connected. So the bottom line is it could be a nearby star, a stellar flyby, as they say, a very close stellar flyby that created a disturbance in the system that disturbed both the disk and somehow caused the planet to have this unusual orientation and great distance from the star. Another possibility is that in the disk around HD 106-906b, the star HD 106-906, there's another planet, HD 106-906c, that we haven't detected yet. And these two planets had interacted with each other in something called planet-planet scattering. A violent interaction where the planetary system becomes unstable, and it's that interaction that ejected the planet we do see to these great distances.
Okay, great. Abi, did you need to add anything to that?
Did you want to add anything to that?
Oh, no, that's about it.
Okay.
No. Yeah.
Okay.
Okay.
The next question also is for Dr. Callis. This comes from Steve Marin former AAS press officer and now freelancing from the Washington, D.C. area. Could you please describe the parameter space relevant for study of exoplanetary systems in which GPi is superior to Hubble, and compare that to the parameter space for studies in which Hubble is better than GPi?
Steve, that's also a good question. Both facilities and their instruments are highly complementary, actually. In the optical, at optical wavelengths, Hubble is superior to everything we have on the ground. It's just a fantastic resource, being above the atmosphere and obtaining these sharp images. It's a smaller telescope, though. It's a 4-meter telescope, whereas Gemini is an 8-meter telescope. So theoretically, a ground-based telescope nowadays can produce a sharper image if we're using adaptive optics, as we do with GPi. As you can see from our press material, the wide field is what Hubble is giving us. And this we cannot do with GPi. GPi and other extreme adaptive optics systems look very close to the star. This is hard to do with Hubble, whereas Hubble can look at the wider field and study the structure and architecture of extrasolar planets farther out. GPi works in the infrared, not in the optical. Hubble also has some infrared capability and used to have a chronograph called NICMOS, which was responsible for many breakthroughs in our field. The two systems are complementary. GPi in the infrared, Hubble has strengths in the ultraviolet and in the optical. GPi is good for getting close in, but cannot study the wider fields. And Hubble, as I've noted, is good for the wider fields.
Okay, thank you very much, Paul. Well, it's 1 o'clock. We've been at this for an hour. I know that those of you in Hawaii have a session to get to soon. I don't see any other questions queued up. We seem to have had a problem where questions weren't able to be asked on the YouTube version of the broadcast, but I've been monitoring my email to see if any questions came in that way, and I haven't seen anything. So I think we're good. I want to thank all of you again for participating. This is the first time that we've tried a AAS press conference with this technology, and it seems to have gone well. For that, I thank all of you, and also especially Scott Idem for his help in getting everybody sorted out. So we do live in very interesting times when it comes to planets in our own solar system and planets in others, and I know that there will be a lot of interesting presentations over the next few days as the Extreme Solar Systems meeting continues. So we look forward to potentially seeing some more news come out of that meeting. Thank you all very much. Congratulations on the interesting and fascinating results that you're achieving, and we look forward to learning more about this topic at the AAS meeting in Florida in January. Thanks very much. Bye-bye, everybody.
Thank you, Rick. Bye-bye.